just as for any new computational tool as we have, like, we can compute the gradient, which is a form of taking a derivative. We should be thinking about what rules, what properties does the gradient have. And so this is computational properties of the gradient. Later on in this section, we'll be talking more about geometric picture properties of the gradient. The first thing to note here is that the gradient of a sum of two vectors is going to be, unsurprisingly, the sum of the gradients. If you have a scalar, a constant c here, and find the gradient of c times your function f, you can pull the c outside of the gradient, c times the gradient of f. If you have the product of two functions of a couple of variables here, f times g, you have there is a product rule that will apply here. F times the gradient of g plus g times the gradient of f. So what do we see here? It just, the gradient is a form of the derivative, and so we should expect this kind of product rule to hold here, where the gradient is playing the role of the derivative. And then finally, a chain rule thing here is if you have some big function f, and into that you plop in some function f of x, little f of xy, this ends up being f prime of x comma y, f prime of little f of xy times the gradient of little f. So this is a version of the chain rule. This one might be the hardest to understand what's going on, and so I'm just going to illustrate it with an example here. So suppose I ask you to find the gradient of x squared plus y squared plus z squared, all of that raised to the 8th power. So in this case, so I wrote this for functions of 2 variables. This is an example of functions of 3 variables, but that shouldn't scare us. So what we have is that little f of x, y, z is equal to x squared plus y squared plus z squared. So this is our inner function. And our outer function, f of, let me use u here, will be u to the 8th. And so what we are being asked to find here, we're being asked to find the gradient of f of little f of x, y, and z here. So the inner function is x squared plus y squared plus z squared. The outer function is u to the 8th. So what does the chain rule tell us right here? Take the derivative of the outside function being u to the 8th, and that would be 8 times something to the 7th, where we leave the inside alone. We leave alone x squared plus y squared plus z squared times the gradient of f. So what is the gradient of little f right here times the gradient of f? So this is 8 times x squared plus y squared plus z squared to the 7th. The gradient of f is a vector. The first entry, the partial derivative of this with respect to x is 2x. Partial derivative of this with respect to y is just 2y, 2z. So it's this function times this vector. We want to write it all inside of one set of vector brackets. We could write this at 16x times x squared plus y squared plus z squared to the 7th, 16y times x squared plus y squared plus z squared to the 7th, and 16z times x squared plus y squared plus z squared to the 7th. So this is how we apply This is the one that maybe is a little bit hard to grok, a little bit hard to understand. I think this example, yeah, once we see this example, it makes sense how this is just the appropriate form of the chain rule right here. Okay,